Do you take the 91 to get here, or do you take the 60?
I take the 60. I live a lot closer to the 60 than.
Yeah, because this 91 was completely closed.
I heard that this one. I heard it on the radio.
So you got lucky. I got lucky too. So some of my classmates live Riverside. They immediately very early, and they said they just slightly beat it. So.
Oh wow.
There was a huge accident, and somebody got killed. So I don't know the details. So I just know it's
Hello.
Hey guys, what's up?
I had a question with regards to the graduation.
Yeah.
So the October 1st exam is just for applying for everything?
Correct.
And
Yes.
so I can still do the advising after October?
Yes. So the advising is different. So the advising. So when you apply to graduate, then what happens is the system marks you as you're going to be graduating soon. And then because of that, they let you register for classes early. But if you need to meet with an advisor, you're going to have a hold on your account. So those things are different. So you apply to graduate and get the early registration date, but until you meet with us, there's going to be a hold on your account. And so you need to meet with us before the registration, not before October 1st.
All right, that sounds good.
Yeah.
So I'll be doing that next week.
Okay. Yeah, sounds good.
So it's on the email says you need to do the graduate.
I know. The email was really confusing, but you just need to apply for graduation.
That's it?
Yes.
Okay.
Yes.
And then should we have a meeting on our account right now?
If you have an odd number seated and you haven't met with an advisor, then you'll have a whole bunch.
Not for the class.
But that's different. That's different. Okay, if you have an even one, then you're.
So eventually we'll need to do it?
No, because normally if you have an even number seated, you meet with the advisor in the spring.
Okay, I did that with Weiss.
Right, but if you have if you're in your graduating semester, so this is your last semester here, then they waive that advising. There's no point for advising. You're already in all the classes that you study, so there's no advice.
So weird. Then why do the odd ones?
It's just administrative. Yeah, if you're an odd number seated, you're kind of unlucky. You have to meet with the advisor. You have to make sure that you're taking the right class in next semester.
Don't we need to it once, like advising once per year?
Once per year, yes. But they make the exception if you're graduating.
Very consistent. Doesn't really matter.
So you don't have to worry about.
Yeah, you don't have to worry about it. If you have an even seaward, you're
Because it says otherwise you won't have the
My cousin used to.
optimal registration thing. So
yeah, but even that, because the classes you're going to be enrolling for are mostly senior level classes. Like no one else, like who else is going to be signing up for 419? Like who else is going to be signing up for 476? So for our students, it doesn't matter too much, but it's good. It's good peace of mind to have that.
okay, I was just worried. I was just panicking. I was like, wait, I didn't know that I had to.
Doctor, there's no way we're finishing up the graduates before next week. So I've done a few, but I haven't done all of them yet. But yeah.
All right, thanks.
Yeah.
I told you that I was having fun with the significant figures.
Yep.
Do you want to do it before the class starts, or do you want to?
Let me write down the learning objectives here, and then I'll take a quick look. And then if it's a bigger issue, I'll take a look after the class.
Yeah. Just my worrisome is if there is a problem with the program, I'll be like, oh, damn, that means the midterm project is going to make it.
Yeah, it's weird. Usually it doesn't have, usually it appreciates more sig figs, but.
I know,
Yeah,
but
I'll
it
take a
didn't
look.
for me. It was giving me a million. PSI. I was just like, what the hell? Yeah, for question 5. Then we have to redesign.
Are you sure?
Actually, what we go ahead.
You take a look. Yep. All right, let me help Charles first.
If it's quick, you can help him.
I don't know. I mean, you asked us to discuss.
So let me go, I'm gonna go ahead and accidentally close it off. But, so let me, I'll go ahead and open them.
Okay.
Come on, you slow folks.
It takes a while. So you said you were trying to set the diameter for the post, right?
Yeah, so let me go ahead and, I just changed it back, so.
Oh, okay.
Because I did the one I can just get 21 PSI and that's it.
Okay.
I can't get it to 25. So it's calculated right now. Wait, that's not right. Last time I did it that, oh, the other thing is I did, wait, that's right. Why did it do it this time? Let me try 55. 55 is what it really started.
Usually when I edit the geometry, I actually close mechanical and then reload it
Yeah,
after I change the geometry.
That's actually won't do anything.
Oh,
So,
yeah, because it has to reload the new geometry too.
which takes more time.
Yeah.
And that's why it was taking me like 3 hours. I'm just like, you
Oh
know
my
what,
gosh.
this was taking forever, so I just stopped.
It definitely should not take 3 hours. If it's taking more than 5 minutes, I think probably Fullerton.
I wrote the note in the answer. I'm just saying, I can't get it exactly.
Okay, you don't have to get it exact.
Right. It depends what kind of boss you have. Some boss can get very OCD.
Oh, okay, I see.
So I had to act like I have OCD too.
Okay, I see. I see.
Every time.
Yeah, see that, okay, so I tried 26, let me see, I tried, last time I tried further down, why is it working? Oh, here's one example, like if you do the max shear stress, it gets really high. But the normal stress is fine, but you were only asking for normal stress, so that's why I ignored.
Okay.
The
Yeah,
max.
the shear stress shouldn't have that much shear.
Yeah, I don't know what's going on.
I mean, it's fine to have some shear. You'll have some, but I think compared to the magnitude of the normal stress should be a lot higher.
Yeah.
Tell me what the normal stress.
Actually, hold on a second. This is completely new. This is the image I got. This was a lot, this was more in the green side of the light green.
It could be that the maximum move. And so, because this, let me see the equivalent stress.
See, and it's also really high too.
Okay, let's see. It's really high when you make it low.
There was,
I mean, it should go up when you make it smaller. And so when you decrease the diameter, you basically make the whole structure a lot weaker. Right? That's intuitively what we believe. And so the way that you see that is that the stresses actually get much higher when you have a thinner geometry. If you increase the diameter, like say right now it's 0.55, right?
Yeah.
And so if you make it like 0.75, then you'll see the stress goes down. And actually, we want the stress to go down because having the stress goes down means that the structure is getting more stable. Right?
Yeah. No, we've only got 2 more minutes. I mean, we can deal with it after, but
Yeah.
and there was sometimes I was trying to do like this.
Okay.
Too.
So the base, what was the base diameter? It was 0.6.
I think so.
Okay. Okay. Yeah, if you increase the diameter, it should make it better. Okay. Yeah. Go ahead and tinker with it a bit more. I'll come by after.
Yeah. And once I find the solution, I found the error, I'll show it to you.
Okay. So.
That is awesome. That is awesome.
It's like,
I'm sorry.
All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? What are you guys doing over there?
They're having a party.
Okay. All right. Okay, so today is Thursday of week 6, and so we're very quickly approaching the midpoint of the semester, which is crazy to think about. All right, so the plan for today, I think today will be relatively chill, okay, and so we're just gonna be looking at all the different element types. So last time what we did is we introduced this idea of the interpolation function, and this is something that's very important to how finite elements operate and behave. Okay, and so we'll go through each of the different element types. We'll look at each of the different element shapes. We'll look at its linear version, its quadratic version, and we'll see how much of a difference that makes. First of all, in the number of nodes per element, and second of all, in what the interpolation function looks like. And we'll talk about some other kind of, I call them practical considerations in terms of what to look out for when choosing an element shape. Okay. Okay. So are there any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get going. And so we're starting with 2D element types. Okay. So, let me start by saying that, when you're looking at an element, it's primarily defined by a few properties. Okay? First, probably the most noticeable property that an element has is its size. And of course, that's the one that we kind of tinker with the most in FEA is, we tinker with the size of the elements and we see how our solution changes relative to that size. Next, we have the shape. And so different, you can choose different shapes for your elements as we've seen in the different ANSYS activities. Okay? And that has an impact, first of all, in terms of what your mesh looks like, but it also has, each shape has its different solution properties as well. Okay. And 3 is the order. And so that's, the order of the interpolating polynomial for that element. Okay. All right, and so for this lecture, we're going to be focusing primarily on these two, because size, just makes them bigger or smaller. But depending on the shape and depending on the order of the element, it's going to change, a lot of things for the element. Okay. And so we're going to start with the 2D elements. You know, I know we don't do too much with 2D in this class, but you know, it's good to start with. Okay. All right, so first let's start with the linear triangle. Right, so the linear triangle is just a simple triangle, and so we have vertices at all the points of the triangle. So we have three nodes or three vertices. Okay. And then for each element type that I'm going to go over today, you know, I'm going to define T of xy, where this is, remember, the interpolating polynomial. Remember, the interpolating polynomial is something that's very important for the element because that determines, you know, the form of the solution, right? Remember, you know, the key thing, or the kind of the unique thing that finite elements does is that before you actually solve for the solution, you have to assume what the form of the solution is going to look like beforehand. Okay, and so that choice of assumption is going to have big impacts on the solution. Okay. And so for a linear triangle, we know that our interpolating polynomial will be a linear function. Okay. And so we have basically the simplest linear function in 2D that we can think of. And so we have a0, which is our constant term, a1x, which is a term that's linear in x, and then a2y, which is a term that's linear in y. Okay. Okay. And remember, you know, the important thing to remember is that the number of terms in our interpolating polynomial matches the number of nodes that we have in the element. The number of terms. That. And so for a linear triangle, we have three nodes. And so we have a node at each of the vertices. And so our polynomial will have three terms associated with it. Okay. All right, any questions on this? Okay. All right, so that's a linear triangle. And so, you know, fairly straightforward. Let's compare that. Actually, let's go to the quadrilateral. So let's compare this to the linear quadrilateral. Okay, so quadrilateral, it's a fancy name for a rectangle. And so our quadrilateral here has four corners. Doesn't really matter what we number them as, but you know, I'm just counting them to let you know that there's four of them. Okay. And so since we have four nodes here, that means our interpolating polynomial will have four terms. Okay. And so, you know, remember what we talked about last time, you know, when you're building up these polynomials, you kind of have to start at the very simplest of terms and then kind of add more terms from there. Okay. And so just like the linear triangle, we're going to start with the pure constant term. Okay. So we have a0. A0 is the same in both polynomials. And so the constant term has no dependence on x, and so it's just kind of by itself. And then we have the pure, what I call the pure linear terms. And so these terms are they just have a single variable. We call them linear because they depend on either x or y, and x or y is raised to the first power. And so we know that when you make a line like y is equal to mx plus b, and so if you have just a single variable by itself, it just makes a straight line. Okay, so that's why we call them linear terms. But of course, this is a quadrilateral, and so we have four nodes here, and so the three terms that we have already is not enough, and so we need one extra term here. But we're a little bit stuck because we kind of exhausted all the linear terms already, and so because this function is only a 2D function, it's only a function of x and y. There's no other linear terms that we can make, because if we say like a3 times 2y, okay, you might think that might be another linear term. But the power of y here is exactly the same as this one, okay? Okay. And so when you're building these, I call these kind of generic polynomials because they have the constants a1, a0, a2, and whatever, all those can be anything we want. And so, when you're building these generic polynomials, all the terms have to be linearly independent of each other. Okay. And so that's kind of a fancy term. I think, for me, whenever I hear terms like that, it gives me PTSD from linear algebra. But all it basically means that all the terms have to have a unique combination of x and y. Okay. And so, this a3 times 2y is not going to work because we already have a y term. So this a3 term has to be unique from all the terms that we have so far. Okay. And so it's an interesting dilemma because we've already exhausted all of the linear terms, and so there's seems like there's nothing else we can do. The only thing we can do is we can just multiply x and y together. And so if we multiply x and y together, this produces a unique term. And so we don't have anything else that's x times y. But at the same time, some people might argue that this is not a linear term in the purest sense. And so what we say is that this term right here is called a pseudo-linear term. Because technically it's not linear because you have two independent variables multiplied by each other. And so we have x times y. And so that itself is not technically linear. But x by itself is linear and y by itself is linear. And so if you combine them together, they're pseudo-linear. Okay. And so that's kind of like a nice little bonus that you get. And so when you use a quadrilateral, you have one more node compared to your triangle, but that one more node actually gives you this pseudo-linear term. Okay? And we'll see later, and we'll see in a bit, when we talk about shear locking, that pseudo-linear term actually gives you some really clutch properties, because even though it's pseudo-linear, it still has some quadratic properties because it's technically a quadratic term. Okay. And yes, kind of is that's the scientific term for it. And so through this, my hope is that you can kind of see why the rectangular elements, the quadrilaterals and the hexahedrons are generally more desirable over the triangular ones, because their interpolation function just has more depth, more rich properties, it has additional terms. Okay? So a little bit long of a bullet point, but that's the reason why. And we'll see this trend kind of continue. And so next we're going to go over the quadratic triangle and the quadratic quadrilateral. Okay, and you'll see the quadratic ones have much more terms associated with it because they're quadratic. But even then, this trend still holds. And so the quadratic quadrilateral have many more terms than the quadratic triangle, and then the same thing for when we get to the 3D elements as well. Okay. So, one way you can think of it is like this. And so remember, in finite elements, what we're doing is we're making an assumption that we know what the solution looks like beforehand. And so if we use a quadratic quadrilateral, and let's say we solve our structural mechanics equation, and we see that there's a strong dependence on x, y. And so, whatever our deformation field looks like, whatever our stress field looks like, if it depends on x, y, then we're going to have a much better job capturing it with the quadrilateral than the triangle, where this term just does not exist for the triangle. Okay. And we'll see, once we finish talking about the quadratic elements, that extra term actually has even better. It helps you prevent, even more stuff. And so, it may seem like an innocuous term, but there's a lot of really good benefits to having that. Right. Question.
Can you create a mesh that has the shape of a pentagon with 5 nodes?
Oh yeah. You can do. I mean, in theory, you can make any element shape that you want. But then you have to write your own software for that. And so ANSYS only has the rectangular and triangular ones kind of built in, but you can make in theory any element for any shape that you want. Yeah, at that point it might get a bit more complicated than calling it just linear and quadratic, because as you can imagine, if you have like a pentagon, there's not, we have the pseudo linear term here, but if you're gonna add a fifth term, it's gonna have some kind of x squared or y squared associated with it. And so it's not gonna be strictly linear, but it's gonna have a lot of nice properties too. The difficulty with those higher, more complicated shapes is actually programming a mesher to actually mesh a CAD model for that. And so a lot of times if you have like a generic, if you have like a predetermined shape, yeah, you can come up with like a pentagon mesh for that. But if you have just like a generic CAD model, it's really hard to make a measure that works with like pentagons and stuff like that. It's the main difficulty with that. All right, any other questions on this? Okay. All right, so let's talk about the quadratic elements. So we'll start with the triangle. Okay. And so for the quadratic triangle, we start with our normal, 3-point triangle. Okay. And naturally you would think that, of course, the quadratic triangle is going to have quadratic terms in its polynomial, right? And so if we start the polynomial, okay, so we'll call it t of xy, just like we do before. Okay, so those are the terms that we had before. Okay. Okay, so we had 3 nodes, and so that's the first 3 terms. And so anytime you build any kind of 2D element, these are the first 3 terms that have to come out first, because remember, we build these polynomials from kind of the ground up. So we start with the constant terms, then we do the linear terms, and then only after we finish all the linear terms can we go to quadratic. Okay. And so you can see here that you might think that we're kind of stuck because we need to get a quadratic function because we're calling this a quadratic triangle, but we don't have enough nodes here to actually make a quadratic function. And so to kind of solve this issue, we have to add some additional nodes to this triangle. Okay. Okay, so all the nodes here are marking in pink. These are called midnodes. And so midnodes, these are basically additional nodes that we can add to the element to increase its order. And typically, you're going to put them, you're not just going to put them randomly in the element. And so a lot of times you're going to put them in somewhat strategic locations. Okay. Most of the time, they're going to be in the middles of edges or in the middles of faces for 3D. Okay. But in 2D, the only places that really make sense to add them are in the middle of the edges. Okay. And so with this, we have node 4, we have node 5, and node 6. Okay. So we added 3 new nodes here for the 3 for the 3 edges. Okay. And now with these 3 nodes added, we can increase the number of terms in our polynomial. Okay, so the first term we're going to add is our pseudo-linear term. And so we have xy, because that's the term that's kind of in between quadratic and linear. Okay, and then we have the terms here that are kind of purely quadratic. So you can see here our interpolating polynomial is looking a lot nicer than it was before because we have these quadratic terms. And as we know, those quadratic terms are going to add more accuracy to our solution. Okay. Because if we have situations where our solution depends on x squared or y squared, we can now capture that with the quadratic element. Okay. And if there's one thing that we know about quadratic terms relative to linear terms, is that they grow a lot more rapidly, right? And so what I mean by that is if we drew a graph here, okay, we know that a linear function will look like this. Okay. Right. So we have just simple x and y here. But for a quadratic function, we know that the quadratic function will go like this. And so one of the big benefits of using quadratic elements over linear ones is that anytime you have rapid changes in your solution variables, whether it be a rapid change in deformation or a rapid change in stress, a quadratic element will be able to capture that a lot more easily. That's one of the primary reasons you would use a quadratic element instance for that. But of course, nothing's free, and so there's actually a very common saying in just computational science in general that there's no free lunch, and so this is no exception. And so generally, anytime that you get something that's more accurate, it's going to cost more. And so in this case, we have twice as many elements here, or twice as many nodes as a linear triangle. And so that means each quadratic triangle will be twice as expensive to compute. And so if you compare a quadratic mesh to a linear mesh, the quadratic mesh is going to take up more memory. It's going to take up more time to compute just because you have more nodes associated with it. Okay. But a lot of times, that extra cost is worth it. And so, especially if you're doing a structural simulation, I'd say 99% of the time, it's usually a good idea to go quadratic. Okay. All right. Any questions on this? Okay. All right. So that's a quadratic triangle. And so now let's round out the 2D elements and go over the quadratic quadrilateral. All right, so just like we did with the triangles, we're going to start with the linear quadrilaterals. I wanted to call them rectangles. And then we're going to add mid nodes. Okay, so we're going to add nodes right in the middle of all the edges. Okay? So in total, we have eight nodes in here. Okay. All right, so that means our polynomial here is going to have 8 terms. And so, there's going to be a lot. Okay. All right. And so, if you compare this interpolating polynomial to the quadratic triangle, of course, we have two additional terms here. Okay. And so we have this x squared y term, and then we have the xy squared term. Okay. And so, of course, these aren't quadratic terms, in technicality, because they have an overall power of 3, right? So x squared times y, and so that's kind of like an overall power of 3. So it's kind of like a cubic term, and then same thing with xy squared. Okay. And so same thing we had with the linear quadrilateral. We'll call these the pseudo quadratic terms. But just like the linear quadrilateral, these terms here, they add a lot of value, because then they add a lot of accuracy, they add a lot of depth to your interpolating polynomial. Okay, so this is exactly the same as before. All right, any questions on the quadratic quadrilateral? Good, I don't have to say quadratic quadrilateral anymore because it's a tongue twister. Okay, so now that's all the 2D elements that we're going to consider. And so before I talk about things like shear locking, let me cover the 3D elements first, and then we'll talk about some of the practical considerations of what you can consider when choosing elements. Okay, so these are 3D elements. Okay, so we're going to proceed with this, in the exact same way we did in 2D, and so we'll start with the linear versions, and then we'll go to the quadratic versions after. Okay, so let's start with the linear tetrahedron. Okay. So remember, a tetrahedron is a 4-sided pyramid. It looks something like this. And then these back 2 nodes here are connected. And so our linear tetrahedron are very, the simplest 3D element has 4 nodes. And so that means our interpolating polynomial will have 4 terms to it. But the important thing now is that because we're in 3D, we're going to have some dependency on z as well. And so we have t of x, y, and z. Okay. So we've entered the 3rd dimension. And so the nice thing about the linear tetrahedron is that its interpolating polynomial is very simple. And so we just go through, we have the constant term as well as all of the pure linear terms. So we have a0 plus a1x plus a2y plus a3z. Okay. And so this is about as simple as it gets. And so, once we start getting quadratic and once we start looking at the hexes, our number of terms here is going to, explode quite a bit. Okay. And I'll say this too. And so, as we go through the rest of the lecture today, it's going to make it seem like that we're going to be constantly dunking on the linear tetrahedron here. But I will say that there's nothing wrong with the linear tetrahedron. So in fact, all the work I did for my dissertation use linear tetrahedrons. And so, there's the tetrahedron has a lot of benefits to it. And the linear one in particular, because of its simplicity, has a lot of benefits too. And all the drawbacks that are associated with the linear element, you can kind of get around that if you're kind of smart in some way. And so, we're going to make it seem like the linear tet is the worst element in 3D. But even that is still a great element. And so you can still do a lot of really good stuff. Okay, and so let's go ahead and let's look at the other linear elements. So let's look at the linear hexahedron. So this is considerably more complex. Okay. And so our linear hexahedron has 8 nodes to it. Okay. And so let's go ahead and write out the 8 terms of our polynomial. Okay, so for our linear hexahedron, we start out with our constant term and all of our pure linear terms. And so we have a1x plus a2y plus a3z. Okay. But of course, we're not done yet because we have 4 more nodes. And so we need to start adding the pseudo linear terms. Okay. So we have a4xy plus a5yz plus a6 xz. Okay, so those are all the tuples, and so those are all the different combinations of 2. Okay. But we're still not done yet because we have 1 more term we need to add, because if you count the terms that we have so far in the polynomial, you only have 7. And so the 8th term is going to seem like cheating because you'll see in a second. Okay. And so the 8th and final term is a very pseudo linear term. It's basically the product of x, y, and z altogether. And so, technically a term like that, because it has 3 variables multiplied by each other, it's technically a cubic term. But we consider it linear because each of the x, y, and z are only raised to the first power. All right, any questions on the quadratic hex? All right, and so let's go ahead and move on. So now we have the quadratic versions of our 3D elements. sorry, we're gonna start with the tetrahedron. Okay, let's go ahead and start by drawing a tetrahedron. Okay, and so we have our 4 initial nodes, right? Right, so we have the nodes at all the corners. But remember, for quadratic elements, we need to add mid nodes in the middles of each of the edges. Okay? And the thing with 3D elements is that there's a lot of edges, and so now in total for the quadratic tetrahedron, we have 10 nodes. And so our interpolating polynomial is going to have 10 terms. Okay, so let's go ahead and write them down. Okay, first we have all of our linear terms. Then we have the pure quadratic terms. And so we have a4 x squared plus a5 y squared plus a6 z squared. Okay. And then we're going to have all the tuples. And so all the pseudo linear terms, but the ones that only have 2 terms. And so we have c7 or a7 xy plus a8 xz plus a9 yz. Equation starting to look like a cheat code in Grand Theft Auto. Yeah, wait till you see the quadratic hexahedron. That one's a doozy. Yeah, it is. You know, they do get pretty long. You know, and it's times like this. You know when you know if you the more you kind of understand the theory of finite elements, the more you kind of appreciate the fact that the computer does most of the work for you. And so, you know, that's especially true for all the math. All right, any questions on this? Okay. All right, so we have one more element to go, and that is the quadratic hexahedron. Bless you. Draw it extra big just so I have space to draw everything. All right, so just like before, we're going to start with all the corner nodes. Okay, so we have 8 corner nodes here. And then just like we did with all the other quadratic elements, we're going to add nodes in between all of the edges. Okay. I'm probably going to miss one, but okay, let's count these up. So we have 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. The last one was in front. Okay. All right, so our quadratic hexahedron has 20 nodes. And you know what that means? That means our interpolating polynomial is going to have 20 terms. And so, we're going to write out 20 terms. Okay. And so, for in the finite element world, the quadratic hexahedron, this is kind of the best type of element that you can get. So this is like, the filet mignon or like the Rolls Royce or like the Whole Foods of finite elements. Okay. Doesn't get much better than this. Okay, so let's go ahead and write it out. We start out with all of our pure linear terms. Then we have our pure quadratic terms. So we have a4 x squared. Okay. All right, then we have our cross terms, and so we have a7 xy plus a8 xz plus a9 yz. Okay. Then we have a10 x squared y plus okay. Yes, we have all the xy combination terms where one of them is squared. Okay. And then finally we have the triple terms. And so we have a16 xyz plus a17 x squared yz plus a18 x y squared z. And finally a19 a y. Too many variables. X, Y, Z squared. All right. Takes up almost an entire page just by itself. So, almost any combination of X and Y that is limited to quadratics, is basically covered in this element. So, any kind of weird stuff, any kind of big variation that your solution is going to do, it's very unlikely that the quadratic hexahedron is going to capture. Okay. But the same rules still apply for all this. And so the more terms that you have, the more accurate you're going to be, of course. But that means you're going to do that many more calculations as well, too. All right, any questions on this? Okay, all right, and so that's all the elements. And so we kind of speed ran that, all that, okay. And so you can see here that, every element, the shape and the order, it dramatically changes what the interpolating polynomial looks like. So, certain element types, certain element shapes have certain terms that are associated with them, and then some of them do not. And so, choosing the right element type, both the shape and the size, of course, and the order, choosing those things carefully for your solution is one of the most important things that you can do with FEA. Okay. And so let's go ahead and talk about that a bit. And so, with all of this selection, in front of us, how do we make kind of the most informed decision, or how do we choose, what type of element to select? Okay. All right, and so, when making a decision on what type of elements to choose, it's always good to kind of remember the general advantages of one form over the other, okay? And so, the way I'm going to format this is, I'm going to kind of format them in terms of like head to head, okay? And so first, let's do the shapes. And so let's do triangular elements. So do triangles / tetrahedrons versus quadrilaterals / hexahedrons. Okay. And so in what situations would you pick triangles? And so the triangles and tetrahedrons have, probably, one of the most valuable properties in finite elements is that they have the simplex property. Remember, what the simplex property says is that you can use triangles or tetrahedrons to mesh any geometry. Okay? Right? And the reason for that is that you can fill literally any 3D space with a combination of triangles and tetrahedrons. Okay? Actually, let me make this a plus because it's a positive. Okay. Well, that's really valuable. So remember what I mentioned before, that I use linear tetrahedrons to do all of my dissertation work. And the reason for that was that I was working with a lot of very unusual and kind of awkward looking geometries. And so I was doing simulations of blood flow essentially. And so, a person's blood vessels are very strange and very awkward looking. So, it was very difficult to get a hexahedron mesh on it. So at one point I was just like, forget it, I'm just going to use tets for this. Okay. One of the downsides to this, though, is that, even though it can mesh any geometry, it may not be the most efficient at doing so. And so it sometimes, depending on the geometry, it takes a lot of elements to fill the space. Okay. And so if you compare a mesh that you can do with tetrahedrons versus hexahedrons, and assuming that you keep the size of the elements the same, what you'll find is that the hexahedron mesh is going to have a lot less elements than the tetrahedron, because the hexahedrons can fill space a lot more efficiently. Okay. All right, and another downside, the one that we saw today is that the triangular elements have less nodes per element. Okay? And what this means is that the interpolating polynomial have less terms. One more positive thing that I'll say, just because it kind of seems we're piling on negatives for the triangles, is that a lot of, I would say, kind of more specialized and more advanced meshing features kind of only really work with triangles. And so I'll say access to advanced meshing features. Okay. Some of you may have experienced this already. So, one, in addition to, the method and sizing objects within ANSYS, another property that we've played around with is mesh refinement. Okay. And some of you have already discovered that if you use mesh refinement on a mesh, it kind of automatically converts the elements to triangular. And so, things like refinement, and if you're doing fluid mechanics, things like boundary layer meshing, those kind of only really work for triangular elements. That's kind of another reason why I stuck with TETs for my research. All right, question. So would a benefit be its ability to run quicker? Yes, yeah, no, I think that would be a good benefit too. And so, because it has less nodes per element, it's going to be less costly to run as well. And so that's true. But kind of the thing that kind of counterbalances that is that even though it has less nodes per element, generally, if you make a mesh with triangle or tetrahedron elements, you're going to end up with more elements. So kind of that cost savings that you get kind of gets canceled out by the fact that you just have way more elements. But that can be a benefit. I'll go ahead and list that. Okay, and so I'd say those are all the pros and cons of using triangular / tetrahedron meshes. Okay. Okay, and so for the hexahedrons, they're going to have kind of the opposite properties. All right, so I think the biggest downside for the quadrilaterals and hexahedrons is that a lot of times you're not going to get it to work for every geometry. Okay. And this is especially true if the geometry has any kind of complexity or curvature to it. So some of you, of course, have experienced this already, having trouble meshing certain geometries. But I will say that there is a way around this. And so, kind of the best and most reliable way to get a hex mesh on something is just to reduce the size. And so if you're kind of hell bent on getting a hex mesh on something, just reduce the size. All right. So and so a positive for quadrilaterals and hexahedrons is that they can fill space very efficiently. Okay. So a hexahedron mesh will fill a space, with less elements than a tetrahedron one. And then also, you'll have the benefit that each element that you create with the hexahedron is going to have more accuracy just because they have more nodes. Okay. Okay. And then, of course, the opposite of that benefit for tetrahedrons is that a lot of advanced meshing features just don't exist for hexahedrons. Okay. Okay. And in fact, and this is one of the marvels of ANSYS itself. And so the fact that ANSYS has such a reliable hexahedron mesher is pretty amazing. And so that's very rare, actually. And so if you go out into the world and use another software other than ANSYS, what you'll see is that you may not even have the option to create a hexahedral mesh, because that's kind of something that ANSYS does really, really well. And it's something that I'm actually consistently impressed with what ANSYS can do, because that's something I didn't have access to, before I started using ANSYS. It's so amazing that even one of my grad students that was doing research with me, we were really struggling to get a good mesh on one of his projects because we were using a research software. But then, I just, thought one day, it's like, let's try to mesh it in ANSYS, and then we'll import that mesh into the software. And it worked like instantaneously. And so he was struggling for like literally months trying to get a good mesh on his project. And then we just threw it into ANSYS, and we got a beautiful mesh like almost immediately. So that was very surprising, and I was very, very impressed. But of course, the downside of having more nodes per element is, you're going to have more cost per element as well. Okay. All right. Any questions on the difference between triangular and rectangular elements? I know we've kind of talked about this before when we did basic meshing, but it's kind of good to go over this in detail because it's a good comparison. Okay, and so that's the comparison between the element shapes. Now let's do a comparison between linear versus quadratic elements. Okay, so linear elements plus, there's less nodes per element. Meaning that they're a lot cheaper, or they're going to be less costly to simulate. Okay. But of course, the downside, the less nodes that you have, the less accurate you're going to be. So I think that was kind of the main point that we were kind of driving home earlier in the lecture today. Okay. Okay. One thing that's unique to structural simulations and linear elements is that you can get something called shear locking. Okay. We're going to go over that in just a little bit, but I want to make sure I mention that here. Okay, and that's something that's kind of unique to structural simulations and linear elements within structural simulations. Okay, and so for this, and it's kind of for this reason that whenever you're running like a static structural simulation, almost always you're going to want to use quadratic elements. Unless you kind of really know what you're doing and you kind of know, in terms of the loads, in terms of the element size and things like that, unless you really have a good knowledge of, what you're doing, most of the time you're going to want to use quadratic because you want to avoid this situation. Okay. And the last thing I'll mention about linear elements is that, if you're not doing a structural simulation, so if you're doing something like a thermal simulation or a fluid simulation like CFD, then linear is actually the preferred option because they are cheaper and you run into a lot less of the issues, with linear in fluids or or thermal sim. Okay, and specifically for fluids. And so this is just kind of trivia. And so in fluids, there's something else that you have to do with the simulation called stabilization. Because fluid simulations tend to get very unstable, so they can blow up in a lot of different ways. And stabilization is a lot easier to do in linear elements than it is in quadratic. And so I think someone must have developed a theory by now of doing stabilization in quadratic, but it's very rare. And so I would say most CFD codes, at least the ones that I've worked with, use linear elements because stabilization is a lot easier. Okay. And so all of the properties for quadratic elements are going to be the opposite of linear, right? And so for quadratic elements, we have more nodes per element. Okay. And so more nodes per element means it's going to be more costly. Okay. But you do the extra work to work out those extra terms, and you're going to get more accuracy. Okay. And this is especially true, like we mentioned before, this is especially true if you expect the solution, either the deformation or the stress, to change rapidly over a small space. Okay. And so another nice benefit to using quadratic elements is that you don't have to worry about shear locking. Okay. So there's not exactly an exact downside to the last point. And so you could very easily run quadratic elements thermal as well. It's just that I would say that a lot of the advanced theory, things like stabilization and things like that, I'd say they're not as developed or they're not as well tested for quadratic elements as linear ones. And so a lot of softwares you'll see outside of ANSYS, especially if you use like an open source research software, just because it's a lot easier, you'll see that they only use linear elements. Okay. Okay. Any questions on this? Okay. All right. And so the last thing I want to go over today is shear locking. So you've probably heard me mention this several times throughout the class, but now we get to finally see what it is. Okay. And so first, let's define, how to observe shear locking, or what are you looking for when shear locking occurs? Okay. And so this is something special that can occur when you have linear elements, specifically linear triangular elements in a structural simulation. Okay. Okay. And when it happens, the way that you kind of observe it is that the elements all kind of lock up. And so the deformations that you simulate, the deformations are going to be really, really low, or they're going to be a lot lower than what you expect. Okay. All right. So why does this occur, and why specifically in linear triangular elements? And so the thing to remember is that when you're running structural simulations, the first thing that you compute are the deformations. Okay? And then from those deformations, then ANSYS will go in and compute a lot of the derived quantities like strain and stress. Okay. And so in particular, I want to focus on strain. Okay. And so remember the way that we compute strain, from a fully 3D deformation field is we take the derivative of the deformation. Okay. And so what do we know about the interpolating polynomials from linear triangular elements? Okay. And so from linear triangular elements, remember they're only comprised of two types of terms. So they're comprised of either a constant term or the purely linear terms. Okay. Okay. And so what happens when you take the derivative of a linear function? You get a constant, right? Okay. And then so by that logic, if the derivative is constant, that means the strain is going to be constant. And if the strain is going to be constant, then the stress is going to be constant. Okay. Right. And so this is a problem. And so, specifically the stress, because, the way that, the deformations are computed, it's kind of an iterative process. And so, first thing, ANSYS will try to solve for the deformation, and then it's going to compute the stress. And then it uses that stress to correct the deformation. So it's kind of like a cyclical cycle. And so if ANSYS sees that the stress is constant within the element, then that constant stress will kind of tend to lock the element up, because you don't have a difference in stress from one end of the element to the other. Okay. Okay. And so that's basically the phenomenon of shear locking. So if you have linear triangular elements in your finite element mesh, then you're going to have constant stresses in all of your elements, and then that constant stress will lock up a lot of the elements. Especially in cases when you have a coarse mesh there. Okay. And so there are ways to fix this, and so you can get a linear triangular mesh to work. You just have to kind of refine the hell out of it. So you just have to make really small elements. And so it can work, but most of the time it's easier just to use quadratic elements in these cases. Okay. All right. Any final questions on this? Okay, all right, and so I think that's kind of a really in-depth review of all the 2D and 3D element types. On Tuesday, we're going to talk about some special elements called shell and beam elements, and then we'll kind of implement them in an activity on Thursday. Okay? All right, so thank you everyone for coming today. Hope you guys have a great weekend, and I'll see you on Tuesday.
Linear execution.
Yes. You can just.
Ryan is the last one, so you can just close it out.
Oh, yeah.
See you guys. Have a good weekend.
When you alter the MATLAB, you just have to change the variables.
Yeah, you change some variables and the mega variables, you have to literally write out like 5 million, not just top.
They change the price.
And that's if we put in column 1 and 2, yes, you have to change.
Yeah, but it was 3 of them.
Yep.
Yeah.
Yeah.
Like in the beginning, it's such a waste of